So addressing problems in many-body quantum mechanics or quantum field theory by brute numerical force is a fairly doomed proposition. Every time you add particles, you have to have new complex numbers for every possible combination of states that those particles can be in. And that really means that you end up with a kind of combinatorically increasing problem. So there's really no way that you're ever going to deal with a reasonable number of modes and a reasonable number of particles at the same time. And that leads us to try and develop some strong approximations. And in fact, there are some major different classes of approximations for doing quantum field theory. Probably the most common in terms of the largest number of physicists doing quantum field theory calculations do it is perturbation theory. If you're describing some interacting particles and the strength of their interaction is quite small, then you can calculate their scattering amplitudes using a truncated power series. The terms in the power series are usually described and enumerated using Feynman diagrams. And there's a tremendous number of details and tricks to using those methods, and they're widely applied in particle physics and some condensed matter physics. But we're going to focus on other tools, because while they're tremendously successful at calculating scattering amplitudes for QED systems, because the dimensionless interaction strength is so small, strong force calculations are typically non-perturbative, apart from some tricks at high energy, and so those calculation methods tend to be less appropriate. And they're also typically suited to probing static properties rather than modeling interesting quantum dynamics. So if we're going to try and do non-trivial calculations that really have some interesting quantum dynamics in them, and we're not going to be able to use perturbation theory, then we're going to have to compromise somewhere, because we've already discovered that the numerical brute force approach is simply not going to work. So one thing you can do in some cases is you can really reduce the number of modes so far that quantum calculations start to become viable again. And this class of systems in which this is most routinely used is in the area called quantum optics, where you look at the interactions between atoms and light. And we will look at a lot of examples like that. And finally, something you can do is you can start to ignore some of the more exotic quantum states that can exist. Typically, when you have a real system, it might be able to go into some entangled state, or it might be able to go into some non-classical state, but the kind of entangled state isn't getting increasingly exotic as you add more modes and more particles. Even though the Hilbert space is growing at some extraordinary rate, the actual space of interesting likely physical states might be a lot smaller, and so you might be able to reduce the complexity in the quantum state. And in this category again, there's an enormous variety of approaches. At the extreme limit of this approach, we return all the way back to classical mechanics, which as we know is an excellent model for the vast majority of states and systems that we encounter. There's a whole spectrum of approaches in between that and the full quantum model, typically with increasing simulation complexity trading off for allowing more interesting quantum effects.